Hello DEFCON, hello AI Village audience. Today is the talk on shell language processing. Briefly about my background in order to give you a feedback why I started research this topic. Right now I'm getting the second master's degree in University of Helsinki in a direction of machine learning applicability to InfoSec, and working as an security data scientist in a vast, applying this knowledge into the industry. If you are interested in the topic, please feel free to reach for an academic article that is released as accompanying to this talk with more details, and of course there is available code as a proof of concept library to implement these ideas in practice. Basically, here we talk about shell as a valuable language. Shell, as opposed to natural languages like English, French, is a constructed language, and but we still can utilize it for similar pipelines as we use for NLP. However, we need to adjust them in an appropriate way. Shell is here for already a noticeable amount of time, about more than 40 years. That's unbelievable. If we see, for example, this screen from Matrix, it's already 20 years past, but we still see here bash commands that are utilized in some way, and it been 20 years ago in pop culture already. So today many enterprises use and collect bash telemetry and other shell telemetry in a centralized way, usually through the ODD services, since it logs the specific syscall execv that basically contains raw commands. But the problem is that this data is still vaguely adapted for machine learning pipelines, at least in public space. If there is any implementations, they are, let's say, Fox knowledge and implemented in particular SOCs or products, and no open research is kind of available. Proprietary research starts to appear. We see, for example, this publication from Elastic or this publication from F-Secure that presents interesting ideas indeed. Please feel free to refer them for additional details. But we still see, we don't see a real scientific evidence in order to utilize this language as part of our pipelines. And but it is used like shell is kind of ubiquitous today. We show it for administrative tasks. Those commands are routinely executed by admins around the globe. Of course, for offensive operations, the penetration testers and real APTs utilize shell commands heavily. And that bringing, for example, those commands do basic network scanning, reverse shell connections, or enumeration of local systems. And of course for defensive analytics, where we collect network traffic or analyze binaries. So basically, ability to utilize shell in a more systematic way using machine learning pipelines is highly valuable for us as a field specialist. For example, applications might be, of course, security analysis, where we detect specific techniques, like, again, what was shown previously, reverse shell connections, system enumeration, persistence mechanisms like changing permissions of files or something that is highly challenging to do in a manual way. There is an unsupervised outlier detection, where we can collect a bunch of data and try to understand which commands differ from other, any clusterization in that space. Here comes as well anomaly detection. If we don't collect commands as is, but collect them with the specific timestamps, the sequence of commands might indicate some specific behavior or system manipulations, and something like command prediction, suggestion, correction is an interesting way to dig into too. Many more. But speaking about predictions, yeah, there is already manual heuristics to do this. For example, cd spell option in bash, or if we look at GitHub's Copilot, we can see how advanced can be generative algorithms, since they already can write a code for you. And we generally can use something similar for shell. If we need, for example, set up a Kubernetes cluster, we can suggest administrator specific commands to proceed with. But what are the challenges? Why we cannot do this right now? Let's take a look on classical NLP pipeline. Here we receive an input as a raw text. Then there happens this magic pre-processing step. For folks outside the industry, it might seem pretty complicated, where we convert specific raw text into an array in some sort, because we need this numerical representation of text in order to feed that into a machine learning model. Since basically any model is an equation, usually a linear algebra, but of course there are more complex algorithms that I mean in scope of linear algebra, of course complex and diversity differs, but and huge emphasis in the industry is how to do the best model, how to utilize the most sophisticated architectures. But in this case we have this array already, and this step in fact does not differ much from classical NLP applications. However, the specifically text processing is a real struggle here. If you, for example, as a member of your team need to implement specific pipeline for processing a shell commands, you will spend 90-95% of time into the pre-processing stage, which is basically more laborious, more adjustable, more variable according to specific environment. And that's what we should focus in case of adjusting a shell commands to machine learning applicability applications. Let's take a look what's in this step. Usually, like in rude manner, we can structurize it in that way. Of course, forgive me, NLP aficionados, you know that there is high malleability in here. Steps can be added and removed, but let's summarize this step in a following way. First of all, there is data cleaning, where we remove all not necessary parts of the data not needed for further analysis. In case of text, it's, for example, lowercasing, removing punctuations if they're not needed, etc. Then happens the tokenization, which basically is splitting a sequence of, again, characters of something into dedicated tokens that shouldn't be split in more depth, because those tokens by themselves are valuable for machine learning model already. And of course there are many techniques that academia experts and industry experts know, for example, name entity recognitions and part of speech tagging, etc., etc. But then after that, if we apply them this additional NLP magic, after that we jump into the encoding, which differs in tremendous ways as well. There are basic techniques like bag of words, or frequency techniques like TF, IDF, as well as sophisticated techniques like current state-of-the-art models in classical NLP transformers. Let's take a look on example how this may happen. We get a text, we clean it, for example, casing, removing all unnecessary punctuations as a question mark. Then we tokenize, and then we encode. In case of classical NLP, we can use already pre-trained models like word-to-vec embeddings that just give us the vector or specific word, and we receive array. In case of, if we apply this sequence to shell, we don't need really data cleaning. I will show you why in a moment, but generally, in case of shell, specific symbols may have a dedicated meaning that we wouldn't like to strip away. But we definitely want to focus on tokenization and encoding. What are the most valuable methods for us to encode data, shell data, rather than just text data. And therefore, we strip away the data cleaning step. For the sake of this talk, let's strip away the additional NLP techniques that we won't dig into deeper, but let's focus on tokenization and encoding only for now. So, what are the problems with the classical NLP techniques when I speak about tokenization? If we apply space tokenizers, like let's split a sequence of commands by spaces, we already see several problems. Some of shell commands may have a space as a part of an individual part of the command. In this case, we see a space as a part of regex for a set interpreter. If we apply, there are more spaces, of course, that are in a gray area. Let's say whether we want to split them or we want to preserve this compactness of this specific token together. If we apply punctuation tokenizer, like splitting by dots, if in case of usual text, this might split the text into sentences, but in case of shell, again, we break many patterns that are valuable for us, regexes again, domain names, etc. If we extend this to any other symbols, we see that there is a bunch of specific values for specific symbols in shell that is hardly interpretable in manual manner. However, it can be done. To be honest, our tokenizer won't be 100% accurate, never, because in case of shell, we literally can have a one-line code within the command, like Python, Ruby. This Ruby example is a reverse shell connection using a Ruby binary. So we cannot reach 100% accuracy in realistic examples. However, we can be fairly good, as we will see in future. To address these problems, there comes actual shell language processing library, which I present as part of this talk. It's based on Bashlex library, which parses shell commands to distinguish important elements of a command from other part of command. However, this specific SLP implementation is adjusted in a way that it interprets some specific crucial moments for machine learning needs better than it's available in case of Bashlex, and solves some of the problems that are present there. And additionally, this library provides an standardized API that allows to achieve encoded command within 4 lines of code as presented on the slide. And this is as easy as it is right the moment. We get this shell command, and which is basically a list of raw commands you can get into Python. and we get an encoded array as an output. And basically, at the moment, we can do stuff. We can play with important visualizations if we want to impress someone, for example, at AI Village talk. We can provide some statistics for management or something. And of course, we can actually feed this data into machine learning pipelines and receive output from models. About this last step, I will talk how this tokenization and encoding library was evaluated. The environment that I've set up was the classification problem, where we have a set of commands that are benign, and we have a set of commands that are malicious. Benign commands consist of NL2 bash dataset. Original paper was published some years ago, and it collected commands from various resources like question and answer portals like Stack Overflow, admin cheat sheets that are valuable in some way, that, for example, comments I showed you in the beginning for administrative needs. But as a malicious commands, we've collected by ourselves specific implementations of some techniques and tools that are implemented for malicious use. Those contain enumeration techniques on Linux services, privilege escalations attempts, reverse shell commands, of course, and most of you that completed, for example, OSCP or done penetration testing in a professional environment will be familiar with these commands, or of course, at least and often the CTF players. So eventually we collected more of several thousand of commands for this evaluation. Since there is data is pretty, like, it's considerable data set, but we don't speak about the big data. Therefore, we needed to utilize some alternative techniques for validation of models. We used cross-validation with the 10 folds. In this image, we show 5 folds. This is technique where you use for training a part of whole data set for specific model training, and you validate your model on the rest of data that you didn't use for training. And you discard the previous models, and with every new fold, you train a new model. And that way, you just take a mean of evaluation metrics across all folds to assess how specific, how precise, what is the performance of specific pipeline. And yeah, here you see the area under the curve and measurement for 10 folds that we implemented. And what are the actual model that we use for training? You would say that we need to train neural networks, right? Because that's cool. But no, like, this is the most prominent mistake that many newcomers do. They just focus on deep learning in the field. However, there is plenty of classical machine learning algorithms that might be more beneficial for fast prototypes or realizations where we just don't face millions or tens of millions of entries of data. So in this case, we used gradient boosted trees, which is a great ensemble implementation of basic decision trees, which basically learns on mistakes of previous classifiers, and with every new iteration, weights the data in a different way. As a result, results are in fact interesting, and we were surprised by them because we see that our tokenizer have better performance, but we didn't predicted that huge margin. For comparison, we used word-punched tokenizer, which is a classical punctuation tokenizer used in NLP, and white space tokenizer, which is often used in for IT needs in modern business environments, like parsing logs, parsing Nginx, Apache logs, etc. And according to this table, you can see that even though precision in all cases is fairly similar, as well as area under the curve, which summarizes the like all the metrics together. However, when we take a look on recall and like F1 score is a harmonic mean between precision and recall. We see like increase by more than of 50% in these metrics. Not sure if we can speak in persons when we refer to the metrics, but for those who don't know the precision and recall evaluation metrics, there is a brief recap on what these metrics represent. Basically, precision is ability of like retrieve is the percentage of the true labels among all the retrieved labels. For example, if classifier says that these 100 comments are bad, then if actually 99 of them were bad, then the precision is 0.99. And the recall, on the contrary, is ability to retrieve from all true real labels the portion of the retrieved comments from actual by model, what model predicts from the real true labels. Again, example might be sufficient. For example, if we have at all 1,000 of malicious commands, if model retrieves 900 of them, then the recall is, if model says that 900 of them are indeed malicious and skips all the last 100, then we see that precision is 0.9. And in this case, referring back to the table, we see that in case of correct tokenization, it is crucial for model to see specific tokens right to be able to retrieve malicious commands. Because if the tokens are too granular, too small, then the ability to retrieve malicious commands from all the malicious command pool is weak. Yeah. So that's the proof that we indeed lack of important research in this direction, and even slightest adjustments to existing techniques can gain like unbelievable boosts to our model performance. Of course, work is just in progress. We should focus, if we speak about this specific implementation of SLP, there are definitely bugs and more testing is needed. It is not yet implemented in any production environment as far as I can tell. And definitely, if you see some imperfections, please feel free to report them. But if we speak about topic in general, we definitely need to investigate more encoding techniques. This example that I've shown you as well evaluated different encoding techniques, and in fact, we didn't notice huge difference between like TF-IDF, label encoding, and one-hot encoding. They all three performed similarly in case of this task. However, one might guess that TF-IDF, which is frequency-based encoding, might be the best. No, they are really differences are too small to favor one over the another, and this might as well show that there is potential in investigation of additional encoding techniques. Again, if we take a look at current state-of-the-art methods in classical NLP, the prevailing part goes to the embeddings and even transformers, which is a more sophisticated deep learning approaches. However, for those techniques we need really a lot of data. So some collection of data sets and furthermore implementation them for embeddings, like training embedding models or transformer models might be sufficient in this direction. Basically, these techniques, they rely on positional relation of tokens within the command. But in case, one might argue that in case of shell, there is no such heavy positional dependence as in case of natural languages. That's true. We can like swap flags with each other, and the command's logic will be the same. However, there are still some parts of the command that depend on the location, and this research direction might reveal indeed valuable ways to encode command. So additional way to represent data in a numerical value might be a character level convolutions, and here I encourage you to refer to this great blog post by Sophos AI team, who show how they utilized character level convolutions to represent then malicious URLs and distinguish them from benign ones. And here, of course, we see similar characteristic patterns with the shell commands, so this direction might be interesting to investigate too. And of course, applications. There are many more models to investigate and the ways to get data, parse data, transform data. So yeah, unsupervised techniques, etc., everything that was described previously. And that's it from my side. Thank you for your attention. If you have any questions, feel free to ask in Discord, or like right now, I'm not sure I will be available right after the talk, but definitely feel free to reach me and discuss those things.